Good evening, gentlemen.
Good evening.
Bonsoir.
Well, we have some good French translation, so we'll keep on our side, on our YouTube channel, we keep in English. You have another channel in French. Let's start with Bill Baker. Bill Baker is a structural engineer, a consulting partner at Skidmore, Owings, and Merrill, some that you can see in my background. Some is the very famous international architecture and engineering design firm. And they are famous, of course, because they had the most famous projects in the world. As a partner, Bill Baker has been involved in numerous projects ranging scale from the engineering to arts installation and to the design of the famous Burj Khalifa in Dubai, which is the tallest structure built by mankind, 160 floor and 828 meter. Bill is heavily involved in research to develop new structural systems and methods of design. So things are always moving based on the belief that geometry is the key to efficient structures. Yes. Current focus of Bill research is developing visual design tools. Bill is also a professor at the University of Cambridge and also lecturing at MIT, Princeton, and Northwestern University. He has received several awards and medals. I won't tell the whole list, is a bit long. But for the anecdote, Bill grew up in a small town in Middle America, and the tallest building there, like an irony of life and activity, the tallest building in the town he was living in was just 3 stories tall. But the city had an interesting architecture, and in high school, he took an aptitude test that indicated a propensity towards engineering. So he did study to be engineer, and he was interested in designing buildings and bridges, excited by this structural engineering. And after starting and working on his study, he later found that his grandfather, who had died decades before his 2 grandfathers, who died decades before he was born, had both been structural engineers. Okay, Bill will show us, we'll have a presentation about 30 minutes, and we have absolutely wonderful slides, and he will go through the slides. Perhaps I will ask some question if there is any question on my side, and then we'll have Ken Lewis. Ken Lewis, so I told you, is in New York City, and Ken Lewis grew up in Philadelphia, where there is a history of and tradition very important for young boys. He is also a managing partner at SUMS, this famous architecture and engineering office based in Chicago and New York City. He started at SUM in '86 after extensive architecture studies at Rhode Island School of Design and Harvard University. With a special focus on New York, he has managed and brought to successful completion many projects of enormous scales, complexity, and visibility, including the award-winning One Columbus Center, which was known as the Time Warner Center previously, the 7 World Trade Center, and of course, the famous One World Trade Center that we all know, and which was built in 6 years after the drama of 9/11, and the opening was in 2011. For the little story about Ken, who speaks a little bit of French, but he won't try tonight because we have separate channels. Ken grew up in Philadelphia, as I told you, and he knew that in this traditional city where history is important, that no building could be taller than the statue of William Penn, which is the Philadelphia founder, on top of the city. So in American City, perhaps we'll have some points, some information about that. There is a rule about how tall you can build a city hall or a capitol, and that even plays nationwide towards compared to what is built, the heights of certain buildings built in Washington, D.C. And for the little anecdote, when he was a kid, he was going with his mother sometimes to a doctor's appointment with eye problems. And one day, suddenly he saw a new tower in Philadelphia and asked his mother, what is this building? I never seen it. And he was very intrigued by this building with giant letters, a lot of horizontal glass windows, something like a factory. And most important for Ken, this building looked like the pile of blocks that he and his brother would build in the ceiling of his house basement. He asked his mother, what was this building? And so it was not new. So a bit intrigued, and shortly thereafter, Ken had a new neighbor when he was still a child. And this neighbor happened just to be an architect, and this architect was very cool. So as we know, in childhood, we have some kind of unconscious influence. The presentation of Ken will be in 4 parts: the history of the site, the designing of an icon, the program with what the One World Trade Center offers, and also a very important point that sustainability, safety, and security, which have been the key rules of building the One World Trade Center after the drama of 9/11. I hope I didn't forget too many things. So we'll have about 30 minutes presentation of both gentlemen. And then, of course, we'll have Q&A, and you can ask for your questions in French or in French, and they will be translated, and I will ask them to Ken Lewis and Bill. So, Bill, if you can take the floor. Unfortunately, you are not in Paris like we hoped because of the pandemic, but you can take the floor with Zoom, and we look at your wonderful presentation.
Well, thank you very much for having me here today, at least virtually. And I'm very pleased to be here today to talk about the Burj Khalifa. And I'll talk about the Burj Khalifa, but I'm also going to talk about it within the, shall I say, the history of mankind and what it represents. We've always, as humans, we've always had this desire to go high, to build things that are tall or to experience great heights. It's part of our culture. You go back to the story of the Tower of Babel, and wanting to build high, or when you go to the mountains, you have to climb the hill to see what it's like, at the top of the hill. Now in tall buildings, there's debate about what is the world's first tall building, but I'm going to talk about the home insurance building a little bit. And it was all of 10 stories tall. It's considered one of the first skyscrapers, built in 1885. And for the thousands of years before these buildings, people lived near the ground where they could walk up. But this building had 2 things that made it different. It had a structural steel frame, so a very distinct structure, and was an elevator building. And so these 2 things, structure and vertical transportation, are the essence that affect the development of tall buildings. Now, so here we are in 1885. Now, it's worth noting that in Paris, just a few years later, something much taller was being built. It wasn't considered a building. It wasn't considered an office building, but the Eiffel Tower certainly, and it wasn't steel, it was iron, but it was certainly some brilliant engineering by Eiffel. Now, the height of buildings approaching the Eiffel Tower occurs early in the 20th century. And then we get to the Burj Khalifa, which opened 11 years ago. And so there's been this huge change, this huge scale in the height of buildings and the buildings, the ability to go high. And if you look at the kind of the history of what the world's tallest building was, you can see that there was a quick run up up until the into the 1930s when you had the Empire State Building, before there the Chrysler Building, these tall buildings, and then there was the hiatus caused by the Great Depression and World War II, and then eventually tall buildings started to be built again in New York and then Chicago and then around the world. But the interesting thing about the Burj Khalifa is that while many of the other buildings going back to the 1930s were just incrementally taller, the Burj Khalifa was remarkably taller. And in light of that, I want to try to get across a couple of ideas, two issues. One is that when you look at a tall building like this building that our firm did, it used to be called the Sears Tower, now it's called the Willis Tower. And if you look at that and you see like thousands of beams and columns, that's too complex. Our brains cannot deal with that. But if you look at that and you say, that's one giant beam coming out of the ground, that's how we think about these things, as if they're one object. They're not many, they're one object made of many parts, but they're really one object. And I pulled this out of our archive at the office. This is a little diagram that was done by the designers, where you can see in the middle, you have these, the building is a series of tubes. It's called a bundled tube. Like there's these 9 tubes that then goes on to 7, then it goes on to 5, then finally 2. And so it's like a giant beam where the shape changes as you go up. And if you look down on the building, it feels like it's a giant a series of boxes put together, these structural boxes which clustered together can resist the wind, and the lines of the columns in one direction act like the webs of a beam, and the cross frames act like flanges on a box beam. And the other thing I want to talk about, issues of scale, but I'm going to introduce that I'm going to talk about this, but I'll talk about it a bit later. It's kind of important to know where the heck is Dubai. Well, it's in the Middle East. It's in the United Arab Emirates. It's one of the few Emirates that doesn't have any oil. So their commodity is trade, and Dubai is to the Middle East kind of what Singapore is to Southeast Asia. It's the place where everyone goes to do business. If you're a business person in one of the surrounding countries, you're likely to have office space in Dubai. It's a very welcoming place. It's very welcoming to people from all over the world. We got involved in the project. We had a competition back in 2003. And this was our competition scheme. And then in 2003, we were off to the races, and we started out with a scheme which was really only this tall. It was 518 meters tall. It quickly grew to 725 meters tall. And finally, the building we built was 828 meters. The change in the height of the building during the design phase was equal to the Eiffel Tower. So if you took the building we started with and you added the Eiffel Tower, you would end up with the building that we eventually built. And it's 828 meters, slightly over a half a mile tall for those who use metric or imperial units. And how big is that? Well, here's what it would look like. Say it was here with me in Chicago, but let's see how it might look around the world. Here it is in New York, near Ken's building at the One World Trade Center, or in Midtown Manhattan near the Empire State Building, or perhaps let's go across the ocean to London in the city, or perhaps at Canary Wharf. But since we're in Paris today, like one could imagine it. In fact, one shouldn't imagine it near the Eiffel Tower. The Eiffel Tower should be left alone and nothing near it. But this is what it would look like if it was next to the Eiffel Tower. Though I have to say, it might look nice in a lot of fonts. It would be an interesting addition to the modern buildings there in a lot of fonts. Here's what it looks like in Dubai, where it is. It's in this city. The city of high rises, which is very much what Dubai is. Now, what I'm going to do is I'm going to give you a little tour of the building. As we said earlier, it's 828 meters tall. In the tower, there's about 280,000 square meters. So it's a big building, but there's bigger buildings out there. But there's also a lot of area in the base, around 186, 190,000 square meters. So the entire construction is in the order of 465,000 square meters, roughly 5 million square feet. So it's a reasonably large project from an area point of view. Now, we'll start in the basements. We have these huge basement floor plates in the order of 50,000 square meters, you know, which have all kinds of base functions. But then you get into the tower proper. And these green levels are the Armani Hotel. And so, you know, the program has these various components. And then, and the shape of the floor plate is not like many buildings, like office buildings. It's a Y-shaped floor plate. And here you have, these are some of the lower floors. If you look at this floor plate, if you were a resident of this, you wouldn't necessarily realize that you have the world's tallest structure above you. And so, you know, here we have the floor plate. I'll talk a little bit more about the arrangement of the building later. Above there are these blue, labeled in blue here. These are some more residential floors, and then there's another zone of residential floors, and the floor plate keeps changing. And then we have another zone of residential floors. Now, what's interesting is several things. Is that each of these zones we treat like separate buildings. Because of issues like with water pressure or voltage drop, you cannot have one mechanical space that services the entire building. It's too much. So from a mechanical and electrical point of view, it's a series of individual, in this case, roughly 30-story buildings that are stacked on top of each other. Another interesting thing is that the client in 2004 sold the blue, the brown, and the yellow, and sold it in 2 nights. It was to these buyers, and these buyers had to put down 50% of the purchase price within 6 months. So one of the things about a residential building, as opposed to an office building, is that they can be somewhat self-financing if there's a market for them. We then continue up here. You know, the floor plates are getting smaller, and then we have these pink levels, which are, believe it or not, office spaces. But they're not office spaces like most of us would work in an office building. But what they are, as I said, you know, Dubai is the center of commerce for that region. So if you're a wealthy individual, you might have an office in Dubai where you do business deals, and that's the nature of these floors at the top of the tower. You know, and as you go up, the floors are, of course, getting smaller. And then in between these colored zones, you have these other levels, which is where all the mechanical systems are. It's where you get your fresh air and your transformers, your fire, and your pumps for your fire protection are all there. And what's interesting in this building is so tall that you actually go through a climate change as you go higher. So these actually pull in the air locally. So you have this efficiency coming from getting you know, high in the sky in a desert climate. I talked about structure, but you know, vertical transportation is essential. Believe it or not, this is the most elevators or lifts we have in any place in the building. There's only 19 shafts, but we have 54 elevators. So a lot of the art of a tall building is how to use this space, and you'll have like shuttle elevators that'll take you to what we call sky lobbies. From the sky lobbies, you go to your local floor. And so this is a mapping of the elevating of the Burj Khalifa. And what you will have is it's like taking an express train. So you might take an express elevator, a shuttle elevator from the ground floor up to say level, you know, 75 or 76. And then you would get in your local elevator that takes you to your individual floor. So the time it takes to get from the ground to your unit, it's around 2 minutes. A lot of times you will take an express elevator, and then you'll take a local elevator to get to an individual floor. And here's what the floor plate is. We actually have stairs in case you have to walk out. But roughly every 30 floors, we'll have something called an area of refuge, where someone can get out of the stairwell and rest if they choose to. And these are protected areas. You know, what made this building possible? Well, luck was a lot of it. Being in the right place at the right time is always helpful. you know, have all your stars in alignment, but there's some technical issues that also made it possible. The structural systems, we did a lot with wind engineering, which is kind of a dominant thing in tall buildings. And then you had to build these things, which are really integration of systems. These are really Swiss watches. And then construction technology. Now let me go back to the issues of scale. I'm going to show you two diagrams here. The one on the left is actually by Galileo. He drew it in 1638. He published it in a book in 1638. And what he said is, if you took the bone on the right there, and you made the animal 3 times as large, and the loads went up proportional to the weight of the animal, this would be the proportion of the bone. So there's issues of scale. And on the right is a very famous book that a lot of architects know called On Growth and Form. It was by a biologist. It's about the reason creatures look like they do is because of the physics of their environment. And this applies to animals where, you know, this is the bone structure of a small mammal. This is a large mammal, but you can't get any bigger because what you need to do is you need to invent a new animal, a new creature. And this applies to tall buildings also, because if you took like the Sears Tower, which is now called the Willis Tower, and you made it twice as tall, you'd have to make it twice as wide. You'd have to make it twice as deep, and the area would go up by 8 times. It would just be too big. The market could never afford it. It'd be too much area. So one of the reasons what we did when we invented this new system, we went up with a system that only scales by the square rather than the cube. If I were to make the Burj Khalifa twice as tall, and I wouldn't do that actually, if I needed to be twice as tall, I'd invent a new system, okay? But if you were to make it twice as tall, it would be, you'd have twice as many floors, and they had to be twice as long, but they wouldn't have to be any wider.
But Bill, how tall could one go?
Well, we're very, very confident that we could easily go twice as tall. It would be a different system, you know, and perhaps even taller. And I think you could build it just as quickly as the Burj Khalifa was built, because we know so much. But the essence of this is understanding issues of scale and issues of gravity and issues of wind. And you have to invent a new animal, because, you know, just as you're not going to take a rabbit and make it the size, the size of a whale, you know, it has to change. And so we would have to create a new species, a new animal to get there.
Bill, did you have to, even if you had so many studies and work before building it, did you have to adjust during the building process?
Oh yes, very, 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 very much so. You know, we started out with an idea, and quite frankly, our first idea didn't work very well. We won the competition. We immediately went into the wind tunnel, and the results were not good. And so we went back and made a bunch of changes in the building, and as we did these changes, the building got better. And the reason it was able to grow by over 300 meters, 310 meters during the design, is because we were kind of lucky that we started off on the wrong foot, because we had to make enough changes that we ended up having something much better. So it was very evolutionary in the design process. In fact, this building here is mainly reinforced concrete with the steel, with a steel spire at the top, and it made of very simple elements like walls and slabs and a few columns. And if I were to do it again, I'd have even fewer columns. But what it was is, we ended up with this system we called the Buttress Core. Now, we only gave it this name late in the game. What we did is you let your ideas flow freely, and you let the design change. And when you think you're about there, try to describe what you've done in words. If it takes a lot of words, you're probably not done. It's too complicated. But sometimes you can get down to just maybe 2 words, a noun plus an adjective. The Sears Tower I showed you earlier is called a bundled tube, 2 words. The Hancock in Chicago is called a braced tube. And this, we looked at, we said what it is, it's a buttress core. And what is it? We have this hexagonal concrete walls in the middle, which surrounds the elevators. And this is a very important, we call this the core. It's a closed shape, it's like an axle. It keeps the building from twisting. So when the wind blows against it, it doesn't twist, but it's too slender to go to such great heights. So what we did is we buttressed it. We put these walls down the corridors, and then we put cross walls between the apartments. And so the center is like a tube you might see in a structure, and the wings are like an I-beam, like you might see in a bridge. And we put them together to create this new system. And one can imagine, let's say the wind is coming in between two of the wings. And so what happens is that third wing buttresses it, embraces it. And so that's the essence of this particular structural solution. And it's important to make things simple and clarify, because if your thinking becomes that clear, you can describe it to your rest of your team. You can describe it to the other disciplines. You can describe it to the contractor, and it helps you resolve conflicts, which always happen when you're designing something complex. And so this man you see here is essentially the same structural system. His leg and his body is this core. He's feeling the wind load against his umbrella, and his back leg is the buttress. And so that's the essence of the system. And the other thing that we do is, just like that man, we push the gravity weight of the building outward and outward. So that the weight of the building helps resist the wind. This is the same thing that Eiffel did. Look how his building, his tower spreads its feet out to be stable. And actually the base of the Eiffel Tower is bigger than the base of the Burj Khalifa. The footprint is wider. And here are Eiffel's calculations. He did these graphical calculations where he's showing how the wind loads will go down the legs and help be resisted by the gravity forces, the weight of the building. And so this is the bottom of the Burj Khalifa. If you walked up to and someone asked you how tall this building is, what would you say? If you knew nothing else, 5 stories, 10 stories? You would probably not guess 160 plus stories. But because of the way we controlled the wind and the shape, even in a storm that happens once every 1,700 years, there is no uplift, there is no tension. The building is as stable as the Eiffel Tower. Now, and Eiffel totally recognized that wind was the dominant thing in tall buildings. It's also dominant and very important in bridge design, which Eiffel did so much of. And so when wind goes past an object, it goes by in kind of an irregular manner, first on one side and then the other. And every time this happens, it causes a pressure differential that makes the building want to rock from side to side. And if a tall building were ever to fall down the wind, it would probably fall down sideways, not in the direction of the wind. And these pulses are like when a child is on a swing set and they kick their feet. And if they kick at the natural harmonics of the swing, they go higher and higher and higher. So that's the problem we're trying to resist or not let happen in the design of the building. So we did a bunch of wind tunnel testing. And what we did is we ended up reshaping the floor plate continually. So instead of that child on the swing having 2 feet that are kicking together, this child has like 27 feet that are all kicking at different rates, and the swing set doesn't go anywhere. And so we did this series of studies. On the far left is our first study, which did not behave very well. And then on the wood one on the right is the intermediate, and the black one on the left is what we built. We actually tested one building that was much taller than the one that we actually built, and it actually did pretty well. We then take whatever vibrations come from the wind, and we tune the building like a musical instrument. And when we get the building to move kind of slowly, it doesn't move the way the wind wants to push it. It moves in a different direction. And we tune these buildings like a musical instrument. And this would happen in the design phase. We had this initial design, which was not very happy. And here we have the base moment, which is like the level of force, and the acceleration, which is how much it moves. And we had the intermediate and then the final building. And you look, even though this building is 310 meters taller than that building, the base wind forces are smaller. And it even moves less. And what was remarkable, the building we didn't build actually had less base moment and even less acceleration. But we weren't able to accommodate this design because it came too late. And there was actually a hot spot around the 40th floor, and we'd already built the 40th floor. So now Eiffel was very much into wind also. He actually turned the Eiffel Tower after the exhibition into a laboratory, and he did all these wind tests. So he would drop objects down these cables and measure the wind resistance. And eventually he actually built a wind tunnel at the base of the Eiffel Tower. And here on the left, you see, which was later moved to another location. But here's Eiffel and his wind tunnel, and here's me in our wind tunnel. We actually have our own wind tunnel also, just like Eiffel. Anyway, so the construction is fairly common components. I once was criticized by I gave a lecture once, and one person in the audience criticized me for using such conventional components like walls and slabs and a few columns. And I was thinking when I was asked that question, I said, well, I actually wanted the building to get built. If you're going to try to get a contractor to give you a price for a building that's taller than anything that's ever been built using a system they've never seen before, your chances of being successful is pretty small. And so we use this magic stuff that we still call concrete, but we should probably give it a new name. You know, this gray stuff, the stuff you walk on the sidewalk has nothing to do with this material that we use in tall buildings. Yes.
Excuse me. Why did you use concrete and no other material?
Well, for this building, a lot of it had to do with the fact that it was residential. Okay, you know that, you know, so your spans, your distances were very small. You're only like maybe 9 to 11 meters from the glass, and so very small. But also, it turns out concrete. These buildings have large vertical loads, and concrete is a very efficient way to take what we call compression. Whereas if you did steel, it'd be much more expensive. Now, Ken's building is primarily an office building, so it has both, and we had steel at the very top. But concrete was the appropriate material for this because of its height and also because of its use. Now, the interesting thing was the contractor wanted to see if they could pump concrete 600 meters in the air, and I was thinking, well, how are you going to figure that out? What they did is they ran piping back and forth across the desert floor until they got a pressure loss equal to 600 meters. And then they tried various different concrete mixes and tried to see if what came out the other end was still concrete. And eventually they came up with a formula for the concrete that was useful. Here's what it looked like. The foundations went in, and then it sat there for several months. While the contractor or the owner, Imar, negotiated with the main contractor to build the building. But look at this. Here you see the desert with nothing around it. And now it's this hugely important commercial urban area. And this was originally, it was a military base. And as you look at some of the later photographs, look how this whole area has changed. Anyway, so the tower construction proper started in April, here in 2005, and then it's up. And these are like vertical factories, where the formwork is jacked up, jacks itself up. The concrete is pumped from the ground, and the only thing you have to pick up with a hook is the rebar cage. And so it was able to go very, very quickly. Unfortunately, the cladding contractor went bankrupt on us, so for a long time I got to see just the structure. But eventually, Far East Aluminum came in and started putting a skin on it, and up it came. We were not able to build the spire on top of the building; it was too high. So what we did is we built it inside the building. We used a good French technology by Fresnay, the VSL. Strand jacks, and so we built the spire in the building and then jacked it into position, and it came out the top of the building. Of course, there's a light bulb on top. If anybody wants to be exciting, they can be the light bulb changer. It is remarkably, it is the lightning rod for Dubai. I've been there on stormy days, and it gets hit by lightning like all the time, but it does no damage because the building is properly grounded. Here's what it looks like. It was finished. It was still a little bit dirty. And then they washed the glass, and it came to life. And you can see how incredible it is. And all that sparkle you see is light that did not go into the building. Plus it has these very sophisticated coatings on the glass, low-E coatings, which allow light to go through but not heat, and or minimizes the heat going through. And so here you see the building at the base and around the base. And then, as I said, it opened on January the 4th, 2010 was the opening. And so we all went to Dubai to watch it. And they announced the height because it was a big secret. And they also changed the name. I knew about the height because I was an engineer, but I did not know about the name change. They even kept that from me. And so they named it after Sheikh Khalifa, who's the president of the United Arab Emirates, the Burj Khalifa. It was formerly called the Burj Dubai, and then it was called the Burj Khalifa. They had this giant fireworks show, and as an engineer, I was sitting there thinking, this is not a good idea. But the building was okay. It wasn't damaged by the fireworks, but it was really quite dramatic. And here it is, some photographs I took from about a little over a year ago before the lockdown. And look how urban this area is. It's no longer the desert, and the building, how it interfaces with the city, how it becomes a marker, the center of the city. It forms a very important role, not just as a building, but as a symbol, like the Eiffel Tower. What would Paris be without the Eiffel Tower? And so, here you have it, and the light changes through the day. It picks up these different colors. It's really quite beautiful. And what's really kind of amazing is how it's changed Dubai. This is the base of the Burj Khalifa every night of the year, because every night they'll have these light shows and fountain shows. There's these incredible fountains in front of the tower, and so people will come to watch the shows and listen to the music, and look at the fountains and look at the tower, and this incredible experience. And the owner's gone in there and changed some lighting so that it can actually become this giant art piece to speak of what is going on in the world today, from the Prime Minister of New Zealand to other events related around the world. So it has truly changed Dubai and created an incredible financial engine for the city of Dubai. So with that, I'd like to say thank you.
Thank you so much, Bill, for this great explanation. There are already, of course, a lot of questions online, but first we'll listen to Ken Lewis, who was the key architect to build the One World Trade Center, which happened to be built, of course, earlier. Ken, the floor is yours.
Great. Let me share my screen. Is that good?
Perfect. Thank you, Ken.
Great. Thank you, Cité. Merci beaucoup for having me today. It's a great pleasure to be here. I'm so delighted to talk about a project that continues to take up a piece of my life. I've worked on this for 20 years. I started working on the project on October 16th of 2001, shortly after 9/11. The city was still recovering from those horrible events, but there was an optimism that was out there that we would come back, that we would rebuild, and that we begin to think immediately. First on a building that was destroyed late in the day on 9/11, a 7 World Trade Center, and then about 5 years later on One World Trade Center. I'm just one person of a huge team. And as you hear from Bill, it's an amazing firm that we work for because it was started by architects and engineers. And the architects can talk about engineering, and the engineers are great architects. So when we began with thinking about the World Trade Center, we had been advisors to the owner of the site, the Silverstein people, and they asked us to begin to think about the site. Now, obviously, there were competitions and discussions about what should happen there, including a scenario where nothing was built there and there was a memorial. But there is a huge financial engine that is New York for both the state and the country. And the types of spaces that were destroyed that day were part of the economy of the city. And it was one of those moments in which you step back and you say, well, let's begin with a palimpsest. Let's look at the city. Let's look at where it comes from. And we began with the map of 18th century New York, which you could see was only occupied in Lower Manhattan. That was the only piece. And prior to that, in the 17th century by the Dutch, it was even smaller area, just the tip of Manhattan. And that's the site. What's most important about that is to realize that part of the site is in the river. And over time, the city, as it developed and grew north, the hills were knocked down, material was pushed into the river, and piers were starting to be built that silt would build up, and slowly but surely the city grew up around the site. And by the mid-19th century, the site was completely enclosed, filled in, but it was still, there was water there. And more and more, the city grew and grew from the tip of Manhattan north. By the 1960s, a lot of the city had been abandoned in Lower Manhattan. And not abandoned, I would say was falling into a certain state of disrepair as the modern city emerged in Midtown, about 40 blocks north of here, around Grand Central, around the Empire State Building, and even further north around Park Avenue as it headed north. But at that time, there were two people who were very much interested in preserving the power of New York, which was both shipping and importing, as well as finance. And they were both named Rockefeller. David Rockefeller, who led the largest bank, Chase Manhattan Bank, and his brother Nelson Rockefeller, who was the governor. And they put together a proposal to save New York by taking over this area that is the World Trade Center. It happens to be called, it was called Radio Row. It's where you went to get your radio and your dishwasher. And it was just parts and things. It wasn't a very successful business area. And the bank, and you can't see, I'm trying to point to it. I'm not sure if you can see my mouse, but over here on the right-hand side was a new headquarters for Chase Manhattan Bank, a modern building also designed by our firm, Skidmore, Owings & Merrill. And the harbor was also being dredged. And so what the proposal was to create an international center for trade called the World Trade Center. It was designed by Minoru Yamasaki in a competition, a brilliant Japanese-American architect. However, when he designed it as if it was a fortress. Again, it wasn't a great area to be in. He raised the buildings up 32 feet, approximately 10 meters, and all of the roads were blocked. It was as if it was a samurai castle. And that's where we were on 9/10/2001. The two great towers and some lower buildings, as well as 7 World Trade Center, a new building to the north. And then 9/11 happened. Our office was located mere blocks away. Bill and some colleagues came down, drove all the way from Chicago to New York to assess the situation. Unfortunately, there was not much to assess or to help. But they were there and they worked with the fire department to, if there was buildings where they could go to and check if there was other potential failures. And that's where we found ourselves. And so we pushed ourselves away. We lost a colleague that day who was at the Trade Center. There was a lot of emotion to it, but we put it aside as professionals. And we began to think about the site and what it meant to us. And the most important thing we wanted to do was reconnect the site with the city by connecting the streets to the north that follow the river, West Street and Greenwich Street, and the streets that were running east to west from what is now the Battery to the financial district to the east on the right-hand side of the image, and reconnect it. And this became the basis for a master plan, as you know, by, sorry, went too quick, by Daniel Libeskind, in which there would be 5 towers around a memorial site that you can go to today, wherein the footprints of the old towers, the destroyed towers, would be left as a memorial, really a symbol of the loss within our city. I'm going the wrong way for some reason. And there on the left side, you see the master plan that was proposed by Daniel, 5 towers and cycling up in a spiral and leading up to the tower on the northwest corner of the site, One World Trade Center. Again, Libeskind's role was to create the master plan, which said what things would go where, where the memorial would be, and how the site would face the city in its new role. And on your right is the final master plan, in which 5 great architects had the opportunity to design the site. The 5th tower is actually only under design right now. On the right, a Japanese, a British, a French, and another British architect were there, as well as SOM, our firm, and the memorial by Michael Arad. And for a while, this is what stood there. Well, how did we get here? We began by looking at symbols and thinking about what a tall building would be. We had lost our symbol in the Twin Towers. And also, we looked across the harbor at your gift to us, the Statue of Liberty. It's a brilliant building that also involved Eiffel in the structure. Well, let's see where we begin here. Let me just go back. So Eiffel, and in the form of the Statue of Liberty, and the Trade Center were the symbol of New York. It's what you recognized no matter where you were. And so we began with a simple exercise, like most people do, a sketch on a piece of paper. And we drew the 2 streets coming through, Greenwich and Fulton, the 2 footprints, and Tower 1, which would take its form and shape from the site. And where the memorial, those fountains that I showed you, would be the void in our city and in our hearts, the tower would be the marker in the sky, reaching up to 1,776 feet, the founding of our country, the date of independence, and also would mark the heights of the old World Trade Center towers, which actually were at 2 different heights, 1,362 feet and 1,368 feet. We never really found out why they weren't the same height, but it became something important to us. Overall, we do get that it's not a particular date. When it's in metric, it's 541 meters high to the top of the tower. The tower itself's form is the same footprint as the old World Trade Center, approximately 60 meters by 60 meters. And the height of the building, I said, is the same, but its form is different. When you look at it from a different angle, you notice the rotated square at the top. It's now a 150-foot square. Why do we do this? And so before I move on, we did it because it creates a dynamic about the building as you move around it. And so when you look at it from another angle, the change is more of a pyramidal shape that's going up. What does a pyramidal shape do? It reminds us, it reminds us of other monuments in the world, including the Washington Monument in Washington, D.C. Well, here's the floor plan. It goes from a square at the top to a square at the bottom with an octagon in the middle, and is changing floors as it goes up. This actually played an important role in our planning, which I'll talk about in a few minutes. And there it is. When David Childs, our design partner, was thinking about this, he thought it was very important that a child would be able to come to New York and do a sketch of the building. And he thought about 2 different monuments, the Capitol, which of course has been in the news lately, and the Washington Monument itself. And he realized that if it was something very detailed like the Capitol, you wouldn't be able to sketch it, because is it made of 2 domes or 3 domes? Is the dome bigger than the base? It's a little more complex. And so he said to himself and said to our team, let's think about this as simple as possible. And the Washington Monument is that. You can sit there and sketch it very quickly, and its form comes to mind and obviously has its symbolic values. We also incorporated the spire at the top of the building, which has a beacon. Some would say a beacon of hope, but the thing we were thinking about was that there were light ships that stood outside the harbor of New York, actually just over the horizon. They would be placed there, and they would flash in sequence in Morse code, the letter N for New York Harbor. And so we integrated that element into the building, and there's a beacon there today. So the program from the top, stepping aside from all the symbolic elements. At the very top of the building is the communications tower, the Spire, which is the broadcast antenna for all of New York City. You can imagine how many television stations and broadcasters we have. It also was a communication tower for electronic news gathering. All those trucks that you see driving around the city following news stories need to broadcast their signals to the top of the highest point, and then that is then broadcast back to the main station, as well as having antennas for police and fire department. Below that is a wonderful ad that you do that used to be there, now called the Observatory, the World Trade Center Observatory, a place where tourists come to the city, spend a lot on a ticket, but it's amazing views both out to the harbor and to the city itself that will never be blocked. None of the other towers can come close to the height, and is actually a sort of delightful day to go up in the building. And then of course, there's really the engine of the building, which is the offices that are in it. We didn't know who would be in the building. And so we had to imagine a person who would be coming to the building. And in this case, it was a young man who was coming to New York. And actually we did it with both a young man and a young woman. We have two versions of this, coming to the city to make their fortune or to participate in all the things that the city has to offer. And we wanted to create a building in which the form and the materiality and even the just vision of it would attract the person, would retain the person, would have the person coming here, as well as look at the different plans. So we had in our mind a law firm, a consulting firm, a financial firm, and actually an architecture firm, though we never could afford to go there. At the middle of the building, as Bill has said, elevatoring is a key component of this. And if we had the elevators serve all the floors in the building, it would be a huge core and create great inefficiency. You wouldn't be able to have any space around that giant core. So we created an intermediate floor, which was called the Sky Lobby, which would be like a lobby in the sky for everybody to come to before they transferred between the low-rise express elevators and the high-rise. And you can see we sort of saw this as possibly a place for runway shows, for fashion events, which have happened. We didn't have any idea that Condé Nast would move into the building along with Vogue and all the great fashion magazines. At the base of the building, a building like any building in this form needs a base, something powerful, something representative of its strength, but also something that needs to breathe. For this building, this is the lungs of the building, and it's a translucent glass wall that has its all electronics like the Burj. It can show digital art. That was our intent, and it's continuously going on, but also needs to feed all the below grade areas with air. It also has multiple entrances, and just going around, there's two office entrances on the north and south side, an entrance on the right to a public park that'll eventually lead to the Performing Arts Center to the east, to the right, and then the observatory entrance, a very different group of people coming to the building that not necessarily want to cross paths with the business people going to meetings in the tower, as they head downstairs to go into the express elevators that come into the building. And this is looking in the lobby where we have another memory element, which is the large core of the building coming down, as if you carved it out of the marble mountain in Italy. We brought along the same stone, the height of the lobby. It's something that we all remember the first time we visited the train center and was coming in. And through both artificial and natural light, we allowed the light to come into the lobby and keep it very simple, along with artwork selected. Below grade is the observation deck entrance, which you see here. You come down, you go around to to North America's fastest elevators. They go 10 meters in a second. You don't really feel it, because it goes slow at the beginning and then it takes off. But basically it means that you can go from the bottom to the observation deck in 30 seconds. That lower level also connects with probably the greenest, most sustainable element of the building, which is the 11 subways and trains that connect to it through the concourse and to the Oculus, as well as over to the Brookfield Place to the west. Now, one component, I'm gonna pause. Friedrich, if you have any questions, I could pause here. I'm not sure.
Let's keep going because there are a lot of questions already.
Okay.
They need more explanation.
Sure.
At this point, but yes, of course. Perhaps to insist, how did you work to? How did you design an icon, and why was it so important?
So we designed an icon in a collaborative environment. There was a team of maybe at the beginning 10 or 11 people that were sitting in a room discussing the characteristics of the building. We were getting information from consultants, some of it very serious, having to do with other threats that might exist. But probably the tool that tied us all together is what you see in this picture here, and it was used by all components of the building, and that is our building information model, what we call the BIM model. And this was the first large-scale project that was using what's called Revit, that's the brand name, in our office, and is now the standard for BIM modeling, certainly in the United States. It involved the structural engineers, the mechanical engineers, and in this picture, the contractors who were figuring out how to erect it using our model to do that. The model was so big that by the end, we couldn't use it. We found out later when we did some diagnosis that it turned out that all the screws were in the doors and all the hinges were on the doors in the model. You don't need that information. So the model itself was 120 gigs of information, which was too much for our computers to handle.
At the time. So now it becomes an essential tool for any skyscrapers.
Any project. All projects that we do, they use BIM. Maybe not a small house, but even then, it's a generational shift. I have a son who is trained as an architect, and for them, it's liquid. They don't see it as anything other than their pencil, as opposed to Bill and I, who sit there with pencil and paper and sketch on top.
And that was a big change with this project.
Yes, that was a big change. As we went through this, the younger members of our team were drawing on the computer and coming back to us with models to look at that we could rotate in 3 dimension, and then we would sketch on top. So this is the structural system, and it's a much more complicated story about safety and security, but it really is a true belts and suspenders project. That's a term of having multiple systems working together to provide safety and security, but also to provide the strength that a building of this scale needs. And in most buildings in New York, they were either one system or the other. They were, prior to this in 7 World Trade Center, they were mostly either concrete or all steel. And what we proposed with our structural engineers, that we have a concrete core at the core of it, at the center of it, and then a moment frame, a perimeter moment frame surrounding it and connecting it together. This building, as Bill has shown, all buildings move. Most buildings at this scale, I can't remember what the ratio is, but a normal building at this scale might move out of balance maybe 5 or 6 feet, one way or the other at 1,500 feet. This building moves 2 feet or less. It doesn't move. It just doesn't, it's far too rigid. Part of that is the concrete that was used here. As you saw at Burj Khalifa, the concrete they were talking about was 9,300 PSI. The concrete here is somewhere between, from the bottom to the top, somewhere between 18,000 and 14 to 12,000 PSI. So it's concrete at another scale.
Explain in very simple terms, can you explain
Sure.
why is it important, this PSI issue?
2 issues, and I'll show one a little bit later, is the strength of the concrete has to handle a huge load, right? It's a massive building, and you don't want the walls too thick. Under normal circumstances, the walls would be maybe 5 or 6 feet wide at the bottom of the building, and by using higher strength concrete, the walls could be thinner. And at the top of the building, and frankly, because of what happened on 9/11, the owner gave a direction that no wall that was protecting key elements, the stairs, the elevators, could be thinner than 2 feet in thickness. So that was the, 60 centimeters in thickness. And so those were the guidelines that the structural engineer had to work with. There was also a requirement that that any 2 columns could be taken out, and there would be minor differential bending, deflection in the floor above. Now think about, I can't say what that is, it's not really it, but it is based on what happened at 9/11. And so 2 columns could be taken out, and the tower would stand, and there would be very minor damage to the building, obviously, by whatever took out those columns. So that's a big part of what the strength is in the building. What it also meant was that every single connection here, especially because it's a moment frame, had to be welded and bolted. That is a much bigger burden on a tower than any other part of it. Forgetting the weight, forgetting the wind, it is a pretty massive effort. We often would see when the building was going up that welders would be on a weld for days on end, just building up these huge welds. This is the main reason that I bring up safety and security. This is a fireman coming up the stairs on 9/11. He's carrying a lot of gear with him. He carries his hose, he carries tools to do the work. And at the same time, people are coming down the stairs. These are two uses and two forces that are going in opposite directions. And so we really asked ourselves, and we engaged with the fire department, the Pompadour, and we met with them on a regular basis. To this day, I remember the smell of the men in their bunker suit, because they sometimes came from other fires to our meetings. And we would sit there, and they were great partners when we were developing the building, obviously because of what they did. So on the top of this picture is a stair, as it would be built under the old code, which is fine, and it's safe, and it's got solid walls. And this is the stair as it's being built at the World Trade Center. It's larger to allow two people, two-way traffic. It has a large shaft at one end, that X that you see there, so that fresh air can be pumped into the stairs. The doors open into the flow of traffic. Inside the stair, there's a cable, a coaxial cable, which is an antenna, so you can call on your phone. There's also a coaxial cable and antenna for the worker, for the first responders, firemen, and police that might be going in the stairs. There's all sorts of, there's an area for someone who may be disabled or someone who needs to take a break as they're climbing in the building. And also a sort of area in the stairs where there's lighting that, should the power go out in the building, will stay on, as well as illuminated tape on the stairs. At the time we designed it, we imagined it would be a light like you see in an airplane that they always tell you in the aisle. That was the idea. Many of these things, which were from the International Building Code, have now become the code of New York City, all because of 9/11. The other piece of this is this core that I'm showing you, and we gave it a name. We call it the Emergency Access Core, and it has a number of key elements in it. Probably the most significant is elevator number 4, which during normal usage could be used for service. This is a service core where the service elevators ride. But during an emergency, it becomes the firefighter's elevator. It's in its own shaft. It has its own ventilation, its own set of doors, one leading to the stair and one leading to the lobby. As we went through this, we talked about all the things that could go wrong in a fire and emergency. And one of the biggest things is water that the firemen spray on the fire, which as soon as it gets in the elevator shaft, it stops the elevators from working. The firemen won't trust them. And so we built in drains into the floor. We raised the sills up a little bit so that in an emergency, the fire department and the firemen could use those large service elevators as basically ambulances to take people out who might be injured, but also to take all of the residents of the occupants of the building down. You'll notice the stair is much smaller. That's because it only serves the firemen. It's not part of the normal egress. There's other elements that are located within this protected core that are about communication and firefighting, including all the standpipes that bring water to the floor. Now, I've talked about security and safety. 2001 was the beginning of the new millennium. It was an important date. We were talking about sustainability and had been for quite a while. And we thought that this building and 7 World Trade Center and all the buildings needed to set a new standard for sustainability. And so we engaged with many, many outside agencies, national and international, to talk about issues. And we talked about issues such as energy and where it was being generated, new forms of energy generated, including fuel cells for an emergency. We talked about all of the construction vehicles that were coming to the site and the dirt and particulate matter that they might put off because they use diesel fuel. And so we created a program at the Trade Center to make it the greenest construction site, the safest construction site, and ultimately the first LEED gold site in the country. Probably the most important thing we did was we rebuilt at the Trade Center. Because of all of these subways that come to Lower Manhattan, people don't have to drive in their gas guzzling smoke pots cars into Lower Manhattan. It's probably the greenest thing, and it's why I believe that tall buildings and large-scale development in urban centers is still the pathway to a greener future. Some of the elements were catalytic converters on the construction equipment. The first time that ultra-low sulfur fuel was used on the sites, which is now a standard in New York City on all construction sites. And then the use of recycled material in the concrete. This is the building of 7 World Trade Center. And as you saw in Bill's, when concrete, there was fly ash that was being used, which is a recycled material that comes out of coal and fuel. These were also, it had to be at least 50% recycled content, the steel. I think we ended up being closer to 80% in terms of the steel that's in the building. And we also began to use a new technique, which is jack forming, which wasn't new in many other places in the world. This is an Italian system in which the formwork is self-jacking up the building, instead of in New York, where they would have workers come in and build the formwork, tear it apart, and move it up to the next floor. Now all the formwork went up inside the building, making it more efficient. One other element, which is sort of part of it, at the Trade Center, we had 2 teams competing. There's 2 halves to our core. And they were the red team and the green team, as you can see here with the pumps. And they were competing as they went up in the building, and they competed to get to the top. The green team lost because the concrete machine had to be replaced about 3/4, and they lost 2 weeks worth of time. Once we got out of the ground, it was pretty much construction as usual. There was one other element that you can't see in this picture, but it was a sandwich shop that was inside the building, right above this platform, where the workers could go and get their sandwiches instead of going all the way down the building and out onto the street, and therefore save time at lunch. We tested the building many, many times. First for the color of the glass, and this is the glass that you see on the building, which one thing I want to point out, this is the biggest pieces of glass at the time that could be manufactured. Prior to the World Trade Center, they were making glass about a foot shorter than this. We tested it for blast, that's the middle one. I can tell you that only 2 lights broke in the blast testing, which was not insignificant, having attended it. And the one on the right is the test for hurricane force winds. And again, the robustness of the building really bore itself out. There were no failures in any of the exterior wall. So when we're looking at the exterior, we're trying to figure out what it is that we would want. And one of the things that we were finding out through all of our practice, in particular our interiors practice, was that people wanted daylight. That daylight, and we were hearing this from them and scientists, that daylight is something that refreshes people, that it was important. That it wouldn't be good if they had tinted glass or shades down all the time. And so we went out and we asked the manufacturers to create a glass that was ultra low iron, I'm gonna go back, that you see here, ultra clear, but also a coating that would go on it that would resist heat gain from the sun. And when you step inside, the visibility is unbelievable. As you can see behind me, that window is the same glass as at the World Trade Center, called ultra low iron glass. And it also has the low emissivity coating on the outside, which is reflective.
How do you call it? Excuse me, we couldn't hear. How do you call it?
Sure. Low emissivity glass coating.
Thank you. Yeah.
Gonna go on. We also use simulations. In a building like the World Trade Center, the population is somewhere between 10 and 15,000 people that are in the building. And with a very small footprint that we had with all those elevators come down, we didn't want to have a situation where people were lining up, especially if there was an emergency and people had to pass through magnetometers, which is what you're seeing in this simulation. You don't see the magnetometers are not out there. You can just walk in the building. There's cameras, there's all sorts of facial recognition software that's outside the building. But we wanted to plan appropriately if that was the case. And we use these simulations. Again, they used our BIM model to do it. Now, building the building is an exercise in itself, but I think that's for another day and how the team did it. Some of the pieces of steel, some of the largest pieces of steel at the bottom weighed in excess of 160,000 pounds. I can't translate that into metric tons. I'll leave that to Bill. And it involved multiple elevators. There's actually 8 elevators that were going up the outside, multiple teams. And by this, the reason for this is that while the steel was going up, the concrete work was coming up, the fireproofing was coming up, all behind it, in order that the building could be occupied as soon as the building was completed. Now, one last component I think is amazing. Some of the pieces were so big, they had to be brought in by barge. This is the Spire coming down the East River and being placed on top. The Spire itself is a building unto itself. It's a little over 400 feet tall and was erected in sequences and ultimately became the cap of the building. Now I'm going to finish with one important point here, and it's the last memory element I'll talk about. When you used to come to New York at the end of the day, the corners of the tower were chamfered. They were on 45 degrees. And it would catch the sun in a way that none of the other buildings in New York catch the sun at the end of the day, both sunrise and sunset. And it would glow, these lines that went up the building. And we took that as a memory element to create a face of the building and the edges of the facades, the segments that you see here, in a beautiful stainless steel that had a particular finish, a laser etch finish. And you can see it here glowing. What we didn't plan on was the actual triangles, the 8 triangles glowing the way it does that you see here in this picture. And when I've been north of the city, many miles north of the city, 40 kilometers or so, you can get up in the morning, go to the train, and you will look down the river and you will see the tower glowing in the distance, as it has become the symbol of New York. Thank you.
Thank you so much, Ken. So we realize now that yes, you built amazing new buildings in a very different environment and very different constraint, except for the gravity, of course, that you have to. So we have already a lot of questions. One of the questions, perhaps I start with Ken, with what you were saying. The history of building it and rebuilding the World Trade Center, was there some idea of rebuilding the same twin towers that were built by your Japanese predecessor, Minuturo Wamazaki?
Yeah, no, there was.
What was behind that? There was a special spirit about the past and the past after trauma.
Sure. So the Yamasaki design was brilliant in many ways. In fact, its structural system, though ultimately led to its downfall, was a brilliant system of a lightweight building. It was one of the lightest high-rise buildings that had ever been done. But the system put the structure at the perimeter of it. And so it was 5 feet of glass, 5 feet of structure, 5 feet of glass, 5 feet of structure all the way around. It was a cage. And so when you had large floor plates of 4,000 square meters, you couldn't get much daylight into it. Second thing is that when you do a high-rise building, the cores drop off, elevators drop off as they go up, and the span, the distance from that core to the perimeter starts to get pretty big. And so by doing what we did was having the walls come in, get smaller as it went up. The smallest floors are 2,500 square meters. The largest ones are 4,000 square meters where the core is larger. We got very efficient floor plates and people get daylight, something on the order of 90% daylight throughout the building.
Before going to a lot of different questions, I have a personal question. Is what is, to both of you perhaps, what is the real purpose of building very high building and skyscrapers? Because in one case we have Manhattan, which is already, as you said, there are so many people and you have to build there because there is even economical need. When we see Dubai, we have plenty of space. So what is the real need to go so high? What for?
Let me take a first stab at that. A lot of it is symbolic. It tells you where the center is. It tells you you know, within a city, you know, this is it. I mean, you know where in New York, you know where downtown is, you know where Midtown is just by looking at the height of the buildings. In Chicago, you know where the center is when you see it. And so, you know, that's a very, very important part of it. And that's more of like an urban planning issue and the like. Now, it doesn't mean you need and a super tall building is also a way to telling to the world I've arrived. Because a tall building is a vote of optimism. You know, pessimistic people do not build the world's tallest buildings. You know, people who you know who are forward, who have hope for the future and the like. You know, is an attribute of the people who strive for these things. So there's definitely an urban point of it. You know, setting your stage for how many people knew where Dubai was before the Burj Khalifas? Not as many as know now because of the Burj Khalifa. But they also can be great economic engines. Like the Burj Khalifa created huge value, and the number of jobs it's created, the like, is just phenomenal. And plus, it goes way beyond just the function of the building. Having said that, just like Paris does not need 2 Eiffel Towers, a lot of times the city doesn't need more than maybe one or a center. You know, you could say, you know, you got in New York, you got Midtown belongs to the Empire State, and downtown belongs to the One World Trade Center. But you know, you don't want to get. They have a very special purpose, but it can be debased if you have too many of them, if you will.
I would say that Burj's motivation, the Dubai motivation, is different than the World Trade Center motivation. Very, very different. I mean, this is an emerging country that ultimately will run out of its main source of income and is transforming itself into a business center for the entire Middle East, a place to go, a place with resorts, and you know, it's a sort of transformation of that whole region and how it works with each other. It's actually a symbol of the collective across the region. It's, in a way, it's a place that represents the whole community that is the Middle East and even further afield. The World Trade Center and the rebuilding of the World Trade Center, probably more importantly, talks about a people's resourcefulness and their resiliency. These events happen, they've always happened, floods and fires and really some horrible calamities. We've just been through one. But I know because of it that we will come back we will work differently, we will be differently, we will design different buildings. I'm talking about the pandemic. But we will come back and we will be together and we will create new things and make new things collectively. For New York to lose a piece of its skyline, it needed to be replaced. It was a loss in our skyline. It was a loss in our heart of those 3,000 people. And so there was a symbolic need for it. I think that story was so telling when we went to present the 7 World Trade Center, our first meeting after 9/11. We were presenting to a community that had the tower fall on them, literally. And their children observed it and they observed it, but they wanted to see that new building come back and to be, frankly, something that looked to the future by being the most sustainable building ever done, a high-rise building ever done, and to be something that gave back to the community in its own way. Now there's other motivations, financial and otherwise, and obligations that the landowner had, but there was very much a symbolic sense of resiliency when we started.
Thank you very much, Ken. But you raised at the same time a second question about the pandemic, which is unfortunately worldwide right now. We see right now in Manhattan much less people in the streets. In Paris too, it's pretty low key. You know, we have curfew and we have people leaving the cities. Do you think, you said somehow that it's reversible. Do you think it will have a long time impact on skyscrapers and huge buildings?
No, and I'll tell you why. I agree with you. The city, that we're in our brand new offices. It's the saddest thing that we're not occupying it because we have to work from home. We do have a group that's in there. But you go out of our building at 5 o'clock, 6 o'clock, And you walk up to Tribeca or anything, and the streets are packed with people going to restaurants, getting together, talking about the business that they did. They need to be together. They will collectively get together to collaborate and to work. Two things. One, the generation that will replace Bill and me, that was coming along now, my son's generation, has grown up working together and collaborating. They work in groups. They live to work in groups. It gives them great satisfaction and frankly, great success. And two, they love the city. They're never going, they can't wait to get back to the city. As much as it's been hard for them to be isolated and separated, the city gives them life, it gives them energy, and it's where culture itself grows from. I'm not saying it can't happen elsewhere. I can't wait to get back. I really can't wait to get back and see my colleagues face to face. Not only to give them that hug, and be glad they've done well, but also to think about our next projects as we go forward.
Bill, do you share this point of view about the impact of the pandemic on architecture? Yeah,
definitely. I mean, it's what we need to do in order to be who we are. It is about, it's the work from home has worked because we all knew each other, okay? But over time, how does a new person become embraced by an organization? It's running into people in the elevator or going out to lunch together. You develop this community, and it's much harder to do that in a virtual world. Will there be more people periodically working remotely? Yes. Yeah. The way we work may be different, but boy, the need for tall buildings and people to work together, is not going to go away.
To meet around the coffee machine is basic, huh?
It's actually, and that's the one. We're very strategic where we put the really good coffee machine, because everybody will go there, and we put up a whiteboard so people can draw their ideas, while they're getting their coffee. It's very important.
There are several questions about the environment. As we know, we have more and more concern about the greenhouse effect and the green innovation in general. What would you say about how recycle can be the skyscrapers that you are conceiving? Do you think already about how to recycle them? And the other question is about the ecological footprint. Yeah. Both go on this matter, which is a big concern, a growing concern.
Well, yeah, sure. We're recycling buildings right now. Of our legacy buildings are being recycled at this very moment. Not turned.
One slide, yes.
Yeah, not torn down, but repurposed. And we've even created, it's called adaptive reuse, to take what are older office buildings and convert them to residential. There's a great debate in New York about, and by the way, adaptive reuse is the greenest thing you can do because of both embodied energy, right? Carbon sequestration. So all the energy, it's something, and Bill, please correct me if I'm wrong. I think it's about 30% of the energy it takes to create all the materials is saved by not rebuilding the building, 30 to 40%. And then the embodied energy, the carbon sequestration that's in a project, depending on the material, is huge, and it stands as to do that. One other thing that we're all doing in our high-rise buildings and super high-rise is trying to look at the future of work and how we will work. It's obviously a digital realm. We all made the switch to Zoom in, I don't know, a weekend or so. It happened very quickly, but it's all of work will be changing in how we get together. I don't see the lack of people sitting around a table and having a discussion. There's so much to the dialogue, and that will change over time, but it will not be gone. I just don't believe it. We're in the midst of a great discussion with many of our clients about well-being and health. It's become so important during the pandemic, how we treat ourselves, how we take the time to renew ourselves on a daily basis. And so health and well-being is coming part of our buildings in a way it never was before, including gyms, and relaxation areas and rooms for quiet time and meditation. And in a way, to give people the break they need and not be the sort of intensive factory floor that it always was, or at least that many people dreaded when they were coming to work.
Bill, you had something to add about the footprint of
I mean, so certainly, you know, there's a lot of research going on in making our materials more sustainable. This is a very important thing. You know, can we actually pull carbon out of the air, not just to make wood, but can we pull carbon out of the air to make concrete, to make aggregate? To go in. And so there's a lot of research that's going on, and it's a very, very important thing. We're all dedicated to you know, the architectural industry has very ambitious guidelines trying to get to net zero as quickly as we can. But you know, the recyclable is important, and even the new buildings we design today, they need to be recyclable as part of the design process. They have to. You know, you can't make it so bespoke that only one user could ever want the building. You know, and we're in this transition area between driving your own automobile versus a different, and so we're actually designing the floor. Say you have a building with parking level. The buildings we're designing now, we're designing those floors to be convertible from a parking floor to an office floor or a residential floor later. In the design we're doing today, even though this is something that won't happen right away. And so it is about designing in, but using the least amount of material to do so. You got to be very efficient, but you also have to design some degree of future ability to adapt the building in the future, because it is the most sustainable thing you can do is not build a new one.
To go to build, we've committed to zero carbon. It's called the 2050 challenge. There's 80-50. There's all these challenges that architects have set out for themselves, including zero waste. And it's, I have to say, the energy, which was when we were building 7 World Trade Center, I think also Burj Khalifa, probably the two things we were talking about was energy and water. You know, that was the focus, given what we were seeing. And now we're thinking about so many different things: the air we breathe, biophilia, and getting materials that are biological, mycelium as one of them, mushrooms as insulation, things that are not just the renewables of wood, but other renewables that can be part of the building.
So in both cases, the Burj Khalifa and the One World Trade Center, if you had to rebuild them today, they would be quite different in terms of environment issues.
I wouldn't say quite different. They'd be incrementally different. Because I mean, we were pretty darn conscious about environment when we were designing them, and we had the high quality systems on there on the skin and everything to really maximize the efficiency. You may not realize this, but Dubai in the summertime is very, very humid, and we actually harvest fresh water from the sky for the building. Now, can we do better? Yes, and I think things are actually going to change a bit in the fairly near future, such as the type of glazing we do. Well, I think will go beyond just reflecting heat to even Ken was actually saying earlier, perhaps generating electricity. Not only do you see through it, but it actually helps to power your building.
Both of you on the same issue: is artificial intelligence coming into the buildings? And you mentioned also the beam, which becomes is this beam also evolving a lot, which is the digital model?
Yeah, I mean, artificial intelligence is it's partially here already. In ways that you wouldn't imagine, from how you build it, how do you stage it, construction, how do you, can your inspection to be sure you built it right, you don't have waste, you don't have to redo, is checked by some some cameras backed up with some artificial intelligence that can spot the errors as they occur. You know, and a firm like SOM, we have so much data from all the buildings we built over the time. You know, we're doing research into using that data to educate machines. You know, so you know there's a lot out there. That I think, yeah, that's something that's coming very quickly, very quickly.
Can you remind us how long it took to build these two major monuments, if you can say, and over time, the technology allows to build more and more quickly?
Sure. It took 6 years for the World Trade Center. We started our design work in 2005. We completed it in 2011. Many of the aspects of the building had to follow some conventional efforts. We also had a train running underneath the building. I think we would have figured out a way to stop the train and we could be more efficient. But the most important thing is we see a future in which robotics is part of the building process. That right now there are actually robots that wash buildings. They come down, they climb down the building. Why couldn't a robot table with a team be walking up and placing the glass or placing the steel? Welding, for the most part, is done robotically in the automotive world. That could also become, but it's not. It doesn't take away the trade, the skills trades. That's not what I'm talking about. Those skills would become operational and these guys would become, in fact, part of our Revit model, where they're working on the model and they're looking at the model as they're doing their work. Many aspects of the building can be done. Prefabrication is happening in all different typologies, where it's done in the factory and it's delivered to the site, ready to go. Many bathrooms are done that way, but I see more and more of that as we go through. Bill?
Yeah, the Burj Khalifa was built in approximately the same time frame. We interviewed for the project in March 2003, you know, and then we had the grand the structure topped out in the January 2009, and then the grand opening was in January 2010. And so it was about the same time. In tall buildings, one of the issues during construction is the wind, and if we do see a future where that's going to be less important, because if it's too windy, you can't use the cranes, you can't do that stuff. So a future where robots crawl up the outside of the building, bringing some pretty heavy lifts. And Ken, your steel there was about I think about 75 tons of steel that one took. Anyway, but if you can have machines that can carry that on the outside, which are not sensitive to the wind, and a lot of construction, a lot of the construction is actually being done off-site. It's going to be done in maybe rural areas to bring jobs to the rural areas, and the site will be more about assembly than it will be about so you say manufacturing. The manufacturing will be done elsewhere.
In the 6 years, do you count the conception in
Yes.
both cases?
Yeah.
Yeah.
Okay. Now we have a question that I was about to forget from young civil engineers or architects. Anaïs in Paris, she asked, what advice would you give to a young civil engineering student who is about to start her career and who is a little bit afraid? How did you feel when you started?
Being afraid is not bad. Okay, it's good to be to anticipate, but also I think it's going to be a time that a young so I'm going to speak of engineers. A young engineer now is going to see a lot of change over their career, but there'll be some things that don't change, and so basic knowledge, a lot of which was of course invented in France. The basics of Navier and others, the basic science will not change. And the more you understand that, the better off you are. I once had a professor who told me that theory is very practical, and I believe that to be true. And so it'll be more about interpretation rather than detailed calculations. It'll be, the computer and we'll be in a post-computational age where you can get results, but what do they mean, and how can you change them, and where's the creativity? I think it's going to be more about creativity and less about just the calculations. But it's going to be an interesting time, and keep learning. Okay, keep doing research, keep learning, because it'll make your life much more interesting, and you may need to do that just to keep up.
I would say I came to SOM. I'm going to give two anecdotes. And I came to SOM and I got into my row. You go into your row where everybody is drafting. And there were two guys and they were screaming all day on the phone. Screaming all day long. What are you doing? How come you can't get it done? They were field guys who were in the office. And they were building housing for the homeless. And they had to get 10 buildings up in a year's time. That was why they were yelling, because they were dedicated to what they were doing. And even though they yelled at me sometimes for just sitting there and working on something pretty, as they say, they have become friends for life. And you will find through this process the greatest friends, because they will inspire you, they will cheer you on the down times, and they will teach you everything you're going to know. You've only learned this much. And you will learn so much by doing the projects that you do. I am so excited for you. I will say one other thing. In 2001, there were people that were saying we should never build tall buildings again because it had been hit by an airplane. I mean, that was the sort of thinking, and had been brought down in such a horrible way. It has been the biggest explosion, I hate to use that word, not literally, a number of tall buildings that have come since 9/11. Exponential growth across the world. Symbolically across China, 20 cities of 10 million or more. It's a transformation we're undergoing. And I envy you at the beginning of your career to be part of that transformation as it takes place.
One question that I started to ask you, but which comes back in more detail, is do you think that tall buildings will get always taller? And what is the real maximum of height? Is it just a question of technological breakthrough to go always higher?
I think the limitation is ambition. You have to have someone who's ambitious enough. As I said, I think you could do one twice as tall as the Burj Khalifa in about the same time frame, and it would be affordable. But I think it's about the ambition, and that it has to make sense. It has to, it can't be a folly. It has to create value, and and it has to be sustainable, and it has to flexibility and future use. But it is definitely possible to go much taller, but it has to be it's a precious coin to be spent carefully, and so it is out there, but it needs to be it's a question not only for individuals but for cities, but also for like a society. Is like, we're going to do this, but this is why we're going to do it. I mean, like the Eiffel Tower is, for me, is like, I can't tell you how many times I refer to the Eiffel Tower as a metaphor for this very question. You could say the Eiffel Tower is a very expensive way to make a restaurant, but it is so much more than that.
I think that to Bill's point, it has to be worthy in its way. We have so many issues that we need to take care of: climate change and resiliency. The public resources are limited, especially coming out of the pandemic. And so I really do see ourselves focused on a number of issues: housing and resiliency, and schools, fixing our schools and making them healthy, better places. But if there's a worthy purpose, and not just as it's superficial, it's somebody's ego that's demanding it, I question it, and I do that seriously. I do know that these big buildings are usually in terms of major cities, they're economic engines. They become the center of a whole community. They are sustainable in that you have 10,000 people who are going through public transit. Maybe ultimately we'll all be having our minds connected or something like that. But at the same time, you know, it has to be worthy of it. And I would say right now, there are many other issues that need our focus and attention. And as you can hear,
Like
we're
what?
talking, well, I would say carbon neutrality, which is about the climate change. Climate change is critical in what we're dealing with. Housing in New York in particular is a critical issue. It doesn't mean we don't build the office buildings. It's not a this or that, but that we take our energies and put them to all the issues that we have to deal with. Look, we've been through the most horrible year here in the United States. We were hit by 3 class 5 hurricanes, right, in the Gulf, which is climate change. What happened this summer, what happened with someone with George Floyd shocked us, and it was here all along and we weren't aware of it. We weren't acting accordingly. And then we had a lack of leadership in our country that in a way that sort of set us all back in a way that just isn't the nature of our place. And so we have to put these things. I believe that architects and engineers make great public servants. They're problem solvers. They should be part of that work, and Bill does this, and I do it. We all do time and do service in keeping with our hopes for our cities and our states and our countries. I'm an optimist. That's what I would say. I'm optimistic.
Good. How, if we take the metaphor of a marriage, how to work, how an engineer and an architect work? Are they a lot of?
Are you next to me, Bill? Can I reach over? Are you right next to me? That's how we work, hand in hand.
Yeah.
Okay.
But it's based on respect.
Yeah.
You know, that you listen to each other, and it helps to be dealing with very creative people. That helps. I never underestimate the creativity of your colleagues. You know, you may have a problem that maybe they can solve it for you. And so it's very much about talking early in the very beginning, before there's a design, because you know people do once something's been drawn, it's sometimes hard to get people to back up. But, you know, it's great to meet when it's a white piece of paper, and everybody's there, not just structural engineers and architects, but you know, interior designers, urban planners, sustainability experts, you know, mechanical, electrical, plumbing experts, vertical transportation. You know, but everyone's there at the beginning, and there's a free flowing of ideas. It's fun, you know. And what? Yeah. Do you have to challenge each other? Yeah, you got to do that, you know. But you do it with from a position of respect.
I would say, you know, this is I'm sure there's a French metaphor for it, but it's like peanut butter and jelly. You know, it's not a great, you know, we go together from the very first day you start working at SOM. You're working with whatever you know, if you're jelly or peanut butter, whatever it is, you're working together to make something better, and you put your minds together, and that's the way you're trained. It is never dictatorial. There is, we've just seen this so many times, putting people together. The other component to it, which obviously in not just this day and age, but every day and age, of the community that you're serving, and engaging with them as a partner, not just an occupant of the building or someone who's paying rent, but as a stakeholder. And those elements, those people, the community and everything have become part of our process from the very beginning. And frankly, it was such a, I've found that to be one of the most rewarding parts of my job as someone who engages with the community many times at many different levels with the community, and going to them and speaking to them from my earliest projects at SOM, which was a hospital. And I learned so much from the people that we're serving, the nurses and doctors, about how to be a great architect.
Sorry, I go back because there is another question about the possibility of recycling these buildings. Are there some parts which are dismountable, where you can, the day you have to put an end to such or such building, to dismount some parts, or to change part when it's for some reason it has to be repaired?
So at the most basic level, we our specifications, the book that tells you what the material is made of and what its characteristics, its specifications, have a component that talks about its recycled content and whether it's recyclable now. It used to be just recycled content, but now it says that it has to be, you have to be able to break it down into components that can be recycled. So if you could see the ceiling in our new office, it is designed to be that way. The base, the substructure is made of recycled content and can also be recycled in that way. The plaster that you see on the walls, the gypsum board can now be recycled. The concrete can be recycled. There are some things I have to say which got ahead of us, which is the glass, because it has the coating and the way it's applied, cannot be recycled in the way that traditional glass was recycled. It has to go through a whole different process. It's one of those things that we might have missed. All the cabling can be stripped. You see it all the time on our sites. All the cabling can be stripped and recycled.
You know, one of the things related to this is modular construction, which has been one of the holy grails of architecture for many times. And it's kind of tied into this off-site manufacturing. And so, you know, we are looking at going forward. It's not as common today where you could actually like just demount a whole panel or something. It has to be shippable. A lot of the world's driven by what you can get on a truck, you know, and the dimensions are somewhat limited as to what you can do, but it will be more and more so. And this goes back to the you know, this whole thing about trying to automate construction to be more so to the extent that it's more of a modular construction that is also demountable, and that's one of the things that we're looking to get more and more on. Now, there will always be bespoke parts which you can't change, but a lot of a building is kind of repetitious, and say it's, you know, 90% repetition and 10% special. Can that 90% be like demountable perhaps and reused if you need to unbuild your building?
There's two parts to this. One is using less material, period, dot. If there's ways that you can do it. And the second thing is what's being called the circular economy. So what do you do? What can this object, whether it's a chair or a table or whatever, and I think frankly industrial design is well ahead of the construction industry, is that you can take it apart in an easy way and all the pieces can be then put back into the stream. Not the waste pile, not a dump or a fire, but actually be reused in some form or another. And that's what we as architects and engineers talk a lot about.
Can you tell us, do you foresee any technological breakthrough? You mentioned, Ken, at some point, the glass, the surface. Are there other breakthrough that you see coming in the next years or the next decades?
Do you want to
go? I can go. I'll just repeat what I said. So what is the barrier between having glass be just transparent and capturing heat and actually it generating energy? And that's physics. So the physics of optics are that the rays will go through the glass, they'll be shifted, and then they continue on. If you could have the glass act as a conductor where the energy from the sun was coming through the glass and taken to a converter that would transmit that energy from solar to electrical, which we can do, right? That's what PVs do, but within the glass in a nanofilm, that would be where we've all headed. Look, when we started 7 World Trade Center in 2001, we were talking about having photovoltaics integrated into the glass. It was the talk of the town. And yet, when we did the analysis, there were many parts of the building that just didn't get this level of sunlight, nor were photovoltaics efficient enough that it would make it worthy and economically worthy. Nowadays, we're seeing photovoltaics, through our research and through use of other materials, including focusing lenses, that you can get up to 40% efficient. We're seeing it change. Batteries, right? The battery world has finally coming into the building world. The batteries at your house will be able to get there. Can you imagine the size of a battery or a battery field in a building like this, what it would look like and what it would go through? I do see one other thing, which I see many things, and that's phase shift materials. And that's the idea that depending on the state of the air that you want to do, whether it's hot air or cold air that you want to bring to a place, or just ambient air, that you would have materials that phase shift accordingly and either reduce, give off cold air, or they give off warm air just by the shift in the material through either chemical, electrical, or just plain old solar reaction. It's distributed, it's gone through it. I can keep going on and on. I could talk about distributed energy. I could talk about on-site generation, but I think those are the ones that are in very, very near term.
Yeah, just the basic materials we use, a lot has to do with the computational power, where people can design materials in ways that are very, very sophisticated. It used to be if you wanted to make a new steel, you'd kind of guess at it, and you go to a foundry and a steel mill, and you put a little bit of this, a little bit of that, and you'd hope what came out would be what you were shooting for. But nowadays they can design this stuff very accurately, and so the properties of the materials that we're seeing, we talked about, reinforced concrete is just a new material, or concrete is a new material. It's unbelievably strong and stiff, based on, and structural steel is getting stronger and more usable, more weldable at high strength. And so all of this stuff is going to make big differences where we don't need to use as much material. It'll be, and the recycled content or the environmental impact of this material is going to be going in the right direction. It's going to be much better. It may be different. Like you may have to do precast elements that have to cure for a month. They have to sit in the yard for a month while the chemical reactions happen. But at the end, what you have is a product that's much more sustainable. So we talk about materials. Artificial intelligence, the way we design and the way we build is going to really change robotics. It's going to be a new industry.
Yeah, I think the one thing that we're both talking about, that both engineers and architects are talking about, is timber. In a big way, in a way that is transformative. We as a firm are trying to figure out a way, and we already have some innovation in that, is to do a timber tower of significant height.
Yeah.
And we can do it now, there's no doubt about it, but we have to find the partners who are ready to do it, and the codes have to change, and that's what we're working on right at this very moment. One, because
that could work for offices and housing.
Yes.
Yes.
The advantages are, which are the advantages?
Well, just you actually store carbon. That's the wonderful thing about timber. Also, timber has a psychological feeling. Some of our clients, in industrial areas, a lot of times we have what we call in the U.S. loft buildings that have heavy timber, and people just love the space. It's the humans connect with timber, and so it's not only good environmentally, but it's also pleasant. It's something that we all. My table here is wooden. That's under my, it feels good. I like it, and so, I think it's multifaceted, the advantages.
Timber is surprisingly flexible and strong at the same time. That's one of those great characteristics that we all talk about, and carbon footprint is probably the biggest thing, but there's so much more to it in that it's an incredibly renewable resource. Right? We can grow and grow and grow, and we won't run out of it.
I have another question. How many years it takes to have the building depreciation?
I'd have to call my tax attorney. But in New York,
does it vary a lot, or is it?
That's a good question for Ken.
So buildings in the United States depreciate depending on the structure of the finances over 39 years. That's the depreciation. I happen to know that. And I hope I probably will get corrected by some American who's watching this, but it depends on the structure of the purchase.
Coming back on the I don't know, 1K, if we can call it a 1K building, which would go higher than 1 kilometer. Do you think that the higher you go, the more you have technological constraints in terms of architecture, which means in other terms that you would have at the end some kind just of a one linear beam instead of having a different architecture?
I think there's still a lot of flexibility, a lot of room for creativity, but it has to be a very disciplined thing. Everything has to be useful, and so you need to deal with all the things we've talked about today. You know, the forces of nature. You know, gravity, wind, seismic. You know, it has to be easily built and quickly built, and so all these things come together. But I still think there's quite a bit of, so I should call it artistic freedom. Another interesting thing is when you go very tall, we talked about this earlier, you go through different climates. I remember going up, I was in Dubai when the building was, when the Burj was under construction. And in July, it's fairly hot and humid, you know, it was, you know, and so at the base of the building, it was very hot, very humid. But we would go up on the outside of the building because it was still under construction. We go on these man hoists, these cages that go up at the outside of the building. And when you got up to about level 50, you could tell it was different. And when you got up to level 160,
yep,
it was pleasant. You know, you didn't move. You were in the same place in the world. You were just a different elevation. And so part of this is, you know, we talk about, we use the term sky source sustainability. It's like you had this snorkel. Can you use this snorkel to go up there and grab a different climate? You know, it's kind of like a little bit like the reverse of a geothermal, you know, where in geothermal, you're putting these wells down into the ground to capture the temperature of the earth. Here, you reach up to the sky to get into a different you know, environment. It's like, I don't know the European example, but in America, if you go to Vancouver in Canada, you'll be down in the valley and it'll be like kind of spring-like, and you can see people skiing on the mountains, you know, right next to you. And so, you know, the elevation is a kind of a remarkable thing. You actually go to a different climate.
Ken Lewis and Bill Baker, thank you very much. We're coming to an end. Thank you so much for your slides to take us in different continents and to make us dream about future skyscrapers and tall buildings. And an important lesson I learned is that simplicity is a very important concept, not only in architecture, so a child can design it, as you said, Ken, but that also technologically, what is difficult, what is tough, is to come to a simple concept, yes, instead, and to be built. So thank you very much for this explanation. And I just have to announce also the next event with the Cité des Sciences. It will be on February 18th, and we'll have the landing of the Mars 2020 rover from NASA, and we'll have a big international event again in the evening of February 18th. Ken and Bill, thank you very much again.
Thank you for having us.
Thank you. Thank you for your excellent moderator. Amazing.
Yes, sir. And Ken and I are going to come to Paris as soon as we can, okay?
Thank
you.
Au revoir.
Bye-bye now.
Bye-bye.